Okay, in this video, we're going to go through Chapter 3, which is entitled Describing Data with Numbers. Okay, the first topic in this chapter is measures of center. So that's what we're going to work on right now. Before we get into that, I want to talk a little bit about this chart right here. So what is this? This is a way of presenting data. We talked about this in the previous chapter, in Chapter 2, and this is a stem and leaf chart. Okay, so it's stem, here's the stem, and leaf chart. Here are the leaves. All right, here's your key. The key is essential. So from the stem and leaf chart, I could list out all my data if I wanted to. So let me kind of start to do that to show you what I mean. Okay, so when you present your data in a stem and leaf chart, you do not lose any of the data. Nothing is combined. You still have all the individual data, and this is how you get it back. Look, when your stem is 0 and your leaf is 7, that means you get a value of 7, and it's 7 feet. When your stem is 1 and the leaf is 6, that value is 16. And then you have 18 and 18 and so on. So I want you to make sure that you understand how to interpret this and that you recognize that you don't lose any of the data by presenting it this way. Okay, now let's go to the measures of center. Okay, there are 3 measures of center. One is mode, and mode is the term found most often. Okay, so that means looking at my stem and leaf chart, I see that I have 3 zeros here. That means I have 3 20s. And I have 3 3s here. That means I have 3 33s. So my mode, this is bimodal, since I have 2 modes. The mode is 20 and 33. And I can read that directly off my chart. Now, you would not say that the mode is 0 and 3, because doing so ignores your stem, which is an integral part of your data. Okay, median. Median is the middle term. Now, notice I have a little asterisk right here. And that's because it's the middle term if you have your data in order, either from low to high or from high to low. Okay, this data is organized in the stem and leaf chart, and therefore it goes from low to high. So if you count all your terms, I believe there are 18 of them. So the middle term is not actually part of the data. So what I'm going to do is I'm going to figure out what number is between number 9 and number 10. So counting 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9. And then let me change my color. Here's 10. Okay, so what number goes between 23 and 24? Remember, it's not 3 and 4, but it's 23 and 24. Okay, the number that's between there, to get it, you just take the average. So 23 plus 24 divided by 2 will get me 23.5. So that median, if I have an even number of data points, the median may not be in your data. Now, when would it be in your data? What if I had a 3 and another 3 where that 4 was? So what if this 4 was instead of 3? Then the median would still be 23, because 23 plus 23 divided by 2 is still 23, and it would be part of your data. Okay, so let me get rid of that 3. All right. Okay, the mean. So I'm going to change colors again. So the mean is the average that you are most accustomed to. You're going to sum all your numbers, okay, that means sum, and then divide by the number in your sample. So in this situation, you would sum up all of these numbers that I have listed here, and then you would divide by 18. And when you do that, I am getting 25.1. So your mean could be a number in your data, or perhaps not. It could be a fraction, it could be a decimal. It just depends on how things fall out when you sum all the terms and divide by the number of terms. Okay, the range. The range is going to be the high value minus the low value. So what's the high value? Well, the high value is 43 minus the low value, which is 7, and that gives you a range, high minus low, of 36. All right? Okay, when we start talking about population values and sample values, they are differentiated. So, just a note to make, if you looked at page 59 in our textbook, when they talk about population values, the example that they show you in the textbook is standard deviation, and you can see that the population is going to have capital letters when you're giving a value in that population, capital letters, and they're going to use Greek letters also. And again, standard deviation is the example. For a sample, which is part of the population, you're going to have small letters. And again, look at the standard deviation example. We'll get to that in a minute. But know that you can tell from the notation whether you are dealing with population values or sample values. Okay? Okay, the next page, we're going to go through the key properties of the mean. And the mean being this mean right here. Okay, so to best describe these key properties, what I decided to do is to give us a set of data. So let's just say we have this simple set of data. So the mean will always be located between the extreme values. So what are the extreme values in this case? Well, the extreme values are going to be 2 as the low and 8 as the high. So the mean will fall somewhere in there. And to get the mean, I'm going to sum all these numbers up and divide by the number in the sample, and I end up getting 30. So 30 divided by, I have 6, so my mean ends up being 5. Okay, and 5 is indeed between 2 and 8, so it satisfies the first property. Okay, the next property, the sum of the deviations from the mean is 0. So that means if you take each of these values and you subtract away the mean, so if I say 6 minus 5, so 6 minus 5, I get a 1. Okay, keep going. 8 minus 5, I get a 3. Next one, 4 minus 5, I get a negative 1. 3 minus 5, I get a negative 2. 7 minus 5, I get a 2. And 2 minus 5, I get a negative 3. Okay, so all of the deviations are in the boxes. So look at what I have. I have a 1 and a negative 1. I have a 3 and a negative 3. I have a 2, a negative 2, and a 2. So if I were to add those numbers up, I'm definitely going to get a 0. Okay, so you can go ahead and do that, but that will work with any set of data that you have. Okay, then the next one, the third key property. The mean does not necessarily equal one of the values that were summed. So the values that are summed are the values in your data set. So my mean was 5, and 5 is not a member of this data set, but yet it is the mean. Okay, the mean can be a fraction or a decimal that has no counterpart in physical reality. So let's say that this data represented the number of buses coming to the school any given hour. Okay, so hour 1, you have 6, then you have 8, 4, 3, 7, 2. So your buses are going to be whole numbers. Let's just say that my mean was 5.1. I cannot say the mean is 5.1 buses. 0.1 bus does not exist. So your mean can be a number that really has no counterpart in physical reality. But it does give you an idea of the central tendencies of your data. Okay, number 5, the fifth property. When one calculates the mean, the value of 0, if it appears, must be taken into account. So let's say, for example, I took our data set and I added one more term, and that term was 0. when I summed it up, I would still have 30, but now I would divide by not 6, but 7, and that would have an impact on the mean. You cannot ignore the zeros. The value of 0 means something in this data set. Okay, and the mean, for the 6 property, the mean is affected by extreme scores. So what are the extremes? The extreme values are the endpoints, okay, the low and the high. If you had, instead of having a 2, for example, I had a 12, clearly that's going to have an impact on the mean. So the individual data values do increase the mean. If you increase one of the data points, you're going to have a higher mean. If you decrease one of the data points, you will have a lower mean overall. Okay, so these are the key properties of the mean, and you should be comfortable with each of these 6. Okay, the weighted mean is a very common expression, and we're very used to working with it, although you don't always think about it as a weighted mean. When you calculate your grade, say for this course, and certain categories are weighted certain ways, that changes your average. You wouldn't just average all the numbers in a row. You have certain weights. So a good example of how to work with weights is from this table. Okay, here is our whole formula, but really you will have a better idea of how to apply this if you look at these grades. So when you get grades of A through D, the value of each of these grades is listed in parentheses. Okay, so those values should be familiar to you. So to figure out what your average is, so what's your average for the semester if these are your classes? So what you would do is you would take, so I'm going to put a W because it's a weighted average. Okay, you would take the D, which is 1, and you would say 1 for the value times 3 for its weight, since you have 3 credit hours. Plus, for statistics, that's a 3 credit course, or that's a 3 for a value because you have a B, and it's also a 3 credit course, so it's weighted heavier than is a 1 credit course, and that's how you weight it, okay, by the weight that's assigned in the credit hours. Okay, for swimming, you have a value of an A, which gives you a 4, but that weight is only a 1. Okay, we're going to continue. Plus, for English, the value of the class was a 1 times a weight of 4, so that's a pretty big weight. And then I'm going to do it this way so that I can have a divisor. I just kind of ran out of room. Plus, the biology is 3 times the weight of 3. You're going to take this whole numerator, all added together, and you're going to divide by the total weights. So that's the total credit hours, which is 14. So if you do this, you should be getting, your numerator is 29. So try that. Make sure you're getting that. Your weight is 14. That gives you a weighted average of 2.1, which is in the C range. And that seems to be reasonable given the grades that you had. So what really pulled things down? Probably the 2 Ds that were in 3 and 4 credit classes respectively. Okay, getting an A in swimming was not enough to balance that out. Okay, and to bring it up above a C. Okay, so that's your weighted mean. And if you think of it in terms of how you would evaluate your semester at school, it will make sense to you, I believe. Okay, let's go on to the next page. Okay, now we're moving into section 3.2, which is entitled Measures of Spread. And the measures of spread give you an indication of the consistency of the data set. Okay, so we talk about spread. You are speaking about, for example, the range, which is the high value minus the low value. That is your range. Okay, so if you had, for example, in our data on the other page, let me just go back and look at that. What did we have for, on page 1? The high was 8 and the low was 2. So if the high is 8 and the low is 2, your range is 6, which is a pretty tight range. Okay, so that means there's not much variation in your data. So given that variation term, it takes us to the next term that we're going to define, which is variance. So variance is an estimate of how much is the spread of the data. Okay, so this is how much is this spread? How does the data vary? Okay, so you're going to first think about the deviation around the mean. Okay, that measures the spread of your data. The variance formula, and there's 2 of them here. If you're dealing with data from a sample, so remember, sample is only part of the population, you're going to use small letters, not capital letters, and not Greek letters. Okay, so that's a small x. This is x bar, which is your average. Okay, and then over n minus 1. For population data, if you want to figure out your variance, this is sigma, and it's sigma squared. That's a Greek letter, so I must be dealing with populations. This is mu, and mu is the average when you have population data. Notice that this x is capitalized. Notice that the n, the number in your sample, is capitalized. Notice over here, the n is small, and you reduce it by 1. So these are the formulas for figuring out the variance. All right, so that's variance for both a sample and a population. Okay, standard deviation, how is that related? Okay, this is available on your graphing calculator under stats. So if you were to run some stats, you'd be able to look at the standard deviation. Now, the standard deviation, look how closely it relates to variance. It is just the square root of the variance. That's your standard deviation. Okay, here's the square root of the population variance. And so here's sigma. Sigma is your variance of the population. Here is S. S is your variance, and it's usually a capital S on your calculator. S is your variance of a sample. Okay, S stands for sample. Sigma is Greek. That means it's the entire population. Okay, that's how you're going to remember those. Okay, we're going to talk about putting things in our graphing calculator on the next page. Okay, so there's lots of good things to talk about here. So first off, you're going to use your calculator, and you're going to put the following information in your L1. That's going to be the 6th grade graders drink per day, and in your L2, which is the 8th graders drinks per day, the number of cans of soda they drink per day. Okay, so what you're going to do is in your graphing calculator, you're going to turn it on first off, and then you're going to go to stat, and you're going to go to edit, and you're going to look at L1. Now, if things are in L1 already, take your up and down cursor and go up until L1 is highlighted, and then hit clear, and then come back down. Doing that should clear out your whole column. Do not hit delete, hit clear. Okay, once you hit clear, then you can type in vertical data for L1 of the data points that we have right here. So when you have them all typed in, let's see how many we should have. You should have 24 students. So you have 24 students involved, and if you type your data incorrectly, checking as you go, you'll have 24 data points. Okay, then let's do the same thing for L2. Take your cursor and go to the right to get to L2, and then go all the way up again. If you have data in there, go up to L2, darken that box, and hit clear. That will eliminate the data. Then you are free to enter all the numbers of cans of soda 8th graders drink per day. And when you do all that, the 8th grade class is a little bigger than the 6th grade class, so you should have, you should have 26 data points. All right? So get that done. And once we have all the data in, we can now work with it. Now, because everything you're going to do from this point forward depends upon this data. It is wise to go back carefully and make sure you didn't miscopy something, because that is really easy to do. Okay, so we want sample standard deviations for each of these. So we're going to first go back to stat. Now we're going to go to calc. We're going to do one var stats, hit enter, and then you see where it says list? You're going to type in L1. And the way you do that is you would say second 1. That gives you L1. Do you see that? Do you see the L1 above your 1 key? So L1 is default on my calculator, so I didn't have to change anything. But if yours does not say L1, you would go to the list and say second L1. Okay, frequency list, you're going to leave blank. Calculate is what you're going to do next. So enter, and you're going to see some flashing going on, and now you're getting all kinds of information. Notice your X bar. Your X bar at the top is your sample average. Okay, we want the sample standard deviation. That is your S sub X. And if you round it to the nearest hundredth, you should be getting 2.02. So this should be 2.02. Okay, now go back and you're going to do the same thing for the 8th graders. So you're going to say stat, you're going to say calc, you're going to say one variable stats, but now you want to plug in L2. So you're going to say second 2, that gives you L2. You're going to hit enter, enter. It's calculating for you. You see the flash, and here you have your X bar. Look down, and you should be getting a standard deviation as well for the population, so write that down. Okay, so if I round to the nearest hundredth, I am getting 3.72. And I think I misspoke a second ago. There are 27 students in this class. Now, I think I may have said 26. So there are 27 students in that class. And I can see that because I can see that N equals 27 on my one variable stats. Okay, so that's a little bit of stats. Now it says use your calculator to graph a histogram for each data set. So you're going to need to use stat plot, which if you look at your calculator is where the F1 is, right? So you're just going to say second stat plot, and you're going to turn, go to hit 1, and then turn plot 1 on. Okay, the kind of plot I want is the third type that looks like a histogram with all those bars connected. So hit enter. I first want to do L1. So I'm going to say second 1, that gives me L1. You can put a frequency in of 1. Okay, if you do that, everything's going to be fine. So have a frequency of 1. That means they're going to value each of these data points by 1. So they're going to build your histogram. Now, when you look at this data, you have to adjust your window accordingly. So I'm looking at the 6th grade data. Look at your window so that I can see where my axis is. I'm going to run my X from -1 all the way to, let's go to 7 so we can see some things. Your X scale is 1. And right now I'm working on my window, and to get my window, I hit the second gray key on top. And I'm editing my window. My Y min, so looking at this, the lower value I have is a 0. The max looks like it's 5. That's the highest value. So why don't I just say 7 again. And now I'm going to say graph. Okay, when I graph it, I see a histogram. And my histogram does not have any gaps. I have no values that are 0. Okay, so if you're going to sketch your histogram, then I'm going to turn this off and I'll sketch it and I'll talk about the final product. Okay, so here's my completed histogram for the 6th graders. So you should have a title. So my title is number of cans drank, right? Okay, and then this is your frequency, and this is your number, and this is by the 6th grade. So I have between 0 and less than 1. That's recorded 1, 2, 3, 4, 5. You see, 1, 2, 3, 4, 5, 6. That should be 6. Let me just fix that in 1 second. Okay, everything's adjusted again. So what's happening is I have the number 0, so 0, greater than or equal to 0, and less than 1, occurring 1, 2, 3, 4, 5, 6 times. Greater than 1, but less than 2, greater than or equal to 1 or less than 2, occurs 4 times. Greater than or equal to 2, but less than 3, occurs 2 times. Greater than or equal to 3, but less than 4, occurs 3 times. Greater than or equal to 4, but less than 5, occurs 4 times. And greater than or equal to 5, but less than 6, occurs 6 times. So this is what's happening with my data and how I can present it as a histogram using my calculator and then sketching the representation from the calculator on my paper. Okay, we're going to do the same thing for the next data set, which is the L2, which is our 8th graders. Now, we have a problem because there are some skips here. Do you see how you have a 13 and a 13, but I don't see a 6, 7, 8, 9, or 10? I have an 11. I have no 12. So I do not want to present it by including every single number. So I'm going to do this as interval data. And your intervals have to be the same width. All right, so I'm going to have to look at my data and analyze it a little bit. And this is what I've come up with. I've come up with, I can run from -1 to 4, 4 to 9, and 9 to 14, get a sense of my data, and not have any gaps. So let me go ahead and present that, and I'll sketch it, and I'll turn this back on so we can talk about it. Okay, so if I'm going to do, this is still number of cans drank. This is my 8th grade. And this is the frequency here. So you would label all of these pieces, have a title, label your axes. Okay, 8th grade numbers. All right, so what I'm seeing is because I have gaps in my data, it's better to do it as intervals so that I have an idea of a histogram. You're not going to have any blanks. So my first category, which is greater than -1, but less than 4, I guess greater than or equal to -1 and less than 4, that's 23 occurrences. Then from 4 to 9, so greater than or equal to 4 and less than 9 is only 1 occurrence. And then greater than or equal to 9, but less than 13, less than 14, that last number should be a 4. So let's fix that. Okay, so let me erase here. Oops, that's not what I wanted to do. Erase there and make that a 14. And I see I have intervals of 5, so that number between 9 and 14 is 3. So that gives me a nice histogram, very different than the histogram I created from my 6th grade data. Okay, so that's 2 good histograms examples, and we can do it with our calculator if you control your window. Okay, let's go on to the next page. Okay, so now we are in section 3.3 entitled Measures of Positions. So you can use the empirical rule if you have a normally distributed data set. Okay, so normally distributed means that you have a bell curve. So this would be a bell curve. Okay, if you have a bell curve, and let me write that correctly. So this is C-U-R-V-E. That means that your data is kind of a smooth representation, and that 68% of the data is within plus and minus 1 standard deviation of the mean. 95% of the data is between plus and minus 2 standard deviations. And you can capture most of your data, so 99.7% will fall between plus and minus 3 standard deviations. So remember standard deviation. So this is 1 standard deviation. That's what we got by taking the square root of variance. So you can get that off of your data that you run on your calculator. Okay, so you can plot your data. Okay, this is going to be the mean, and then you're going to work on standard deviations from that mean. Okay, in this situation, our mean was 0. That's not always the case. Okay, so next thing we want to talk about. The bell curve is not the only distribution we could have of our data. This is another theorem, and so this theorem, Chebyshev's, I believe is how it's pronounced, Chebyshev's theorem tells us that sometimes you have not just one max, but perhaps 2 maxes. And so this gives you another way to look at your data. It's not all bell curved. If your data, when you plot it, looks more like this pattern, then you would not be using the bell curve to describe your data. All right, we're going to use a bell curve for lots of our work, and we're going to tie the bell curve into a z-score, which is very important for stats, and we're going to talk about that on the next page. Okay, the z-score is a measure of position that tells you how many standard deviations a particular data item is away from the mean of the data, assuming that your set is normally distributed. All right, so that is key. It has to be normally distributed. So you can turn scores into z-scores, and the way you do that is this way. So if you have all your scores, so say you have a class of 8, and you have these 8 scores, and you want to talk about z-scores, what you would first do is figure out your mean. Your mean is your x bar, because this is just your little sample. So x bar, if I added all these scores up and divided by the number of students that I have, I would get a mean of 33.9. So just do that, make sure that you're getting the same thing I am. If you put this data in your graphing calculator, in your L1, and ran it, you'd be able to read the x bar and the standard deviation, which is going to be the capital S of x. Okay, that standard deviation would be 14.5. Given that, I can now calculate my z-score. So if my score was 14, to get the z-score, I would say 14 minus 33.9 divided by 14.5, and my z-score would be negative 1.37. Okay, do the next one. Student 2 is 31, so you would say 31 minus 33.9 divided by the standard deviation of 14.5, and you get negative 0.2. So let me turn off the speaker again, and I'll fill in the rest of the z-scores, and then we'll discuss them in terms of the grades. Okay, so everything's filled in. So you should be able to do the same thing I just did and get the same values I did. So make sure that you can do that using this z-score calculation. So things that you should note. If your z-score is positive, you must be above the average being the mean. If your z-score is negative, you must be below the mean, or the average of 33.9. Okay, now let's go back up and we're going to read this, and we're going to label our bell curve with the correct information. So it says grades are often assigned based on z-scores in the following fashion. C is given for grades that are within 1 standard deviation of the mean. So if this is your mean, okay, that's your mean, within one standard deviation of the mean is going to be a C. So the C's are going to be from here to here. So slightly above, slightly below the class average. Okay, so the mean in our situation would be 33.9. Okay, let's keep going. A B is given for grades that are above 1 and up to 2 standard deviations above the mean. So above the 1 and up to 2 is going to be a B. An A is given for grades that are above 2 standard deviations. So here is where my A is going to be. Okay, then a D is given for grades that are between 1 and 2 standard deviations below the mean. That means they're going to be negative. So this is going to be my D right here. And F is given for grades that are below 2 standard deviations below the mean, so negative. So it has to be greater than negative or less than negative 2. So looking at this, I don't see any F's, but I do see some D's. So let's fill in our grades. I'm going to fill them in, see if you can fill them in as well. Okay, negative 1.7 should be a D. Negative 0.2, you're pretty close to that mean, is a C. Negative 0.5 is a C. Positive 0.08 is also a C. Positive 0.42 is a C. Okay, 1.52 is a B. Remember, you have to be over 2 to have an A. 1.11 is also a B. Negative 1.03, that's going to be a D. So that's how you relate Z-scores to the bell curve. Okay, it's a nice, neat, systematic approach, assuming that your data is normally distributed. And that is an assumption. If your data is not in the shape of a bell curve, then you really can't use this method of Z-scores. Okay, this page represents another way to represent your data, and it's box and whisker plots, and that's our next topic. So 3.4 covers box and whisker plots. So box and whisker plots rely upon a 5-number summary. So the 5 numbers are your lower extreme, your lower quartile, your median, your upper quartile, and your upper extreme. Okay, so that's what we're working on here. So in our situation, the lower extreme, so let me just make sure I'm seeing what I'm doing here. Okay, so a couple of things I want to tell you. I haven't really told you your data, but you can read it off of this chart. Okay, here's a point right here. It looks like maybe it is like 16 or so. Here is a value right here. Maybe it's about 51 or 52. Here's your median, which is the middle of your data. It looks maybe about 67. The upper quartile, let me just get rid of that. The upper quartile looks like maybe it's 87. And the upper extreme, which is the highest point of your data, looks like it's about 100. Okay, the only numbers that I know are definitely in my data, or I can definitely see the lower extreme, and I can definitely see the upper extreme. So I can do the range also from this, can't I? So 100 minus 16 would be my range. Okay, the upper quartile minus the lower quartile right here. So this minus this will give you the interquartile range. Interquartile range, which is your IQR. Okay, to identify an outlier. So you're looking kind of, let's see what I want to say. Okay, so this, let me just label some more things for you. This is Q1. This is Q2, which is your median. This is Q3. Okay, those have numbers associated with it. Then you have your low and your high. Okay, if you want to figure out if you have an unusually low or an unusually high data point in this data, that is called an outlier. To identify if you have an outlier, you would figure out if you have a high-end outlier by taking the Q3, which in this situation is 87, and then adding 1.5 times the interquartile range. If that number was less than 100, then I would say that my 100 is an outlier. Okay? Let's look at a lower outlier. You take your Q1, which is 51 in this case, and then 51 minus 1.5 times that interquartile range, which happens to be 36, by the way. If you got a number that was greater than 16, then that would mean that 16 was an outlier. Okay, we don't have an outlier in this situation, I don't believe. But check that and see whether I'm saying a true statement or not. Okay, so I just went and I calculated the upper limit, and the upper limit I'm getting is 144 by saying 87 plus 1.5 times 36. And since my upper data point is 100, it is not an outlier. To determine what my lower outlier could be, I take my 51 and I subtract 1.5 times 36, and I get a value of -3. And since 16 is clearly above -3, I neither have an upper outlier nor a lower outlier. So let's talk about another data set and see if you can understand how to use your TI-84 to do the box and whiskers plot. Okay, so here is a data set, and I want you to make a box and whiskers plot for this. So you can put this data into L1, and then once you do that, you would say second stat plot, and still you can go to number 1, and you can see that in terms of types, the 1, 2, 3, the fourth type of data display is a box and whiskers that shows outliers. The fifth type is a box and whiskers display that does not show outliers. Okay, and you can see where you can put your X list in. So if I'm going to do a box and whiskers, my frequency can also still be 1, and my X list is L1. Now, when you do this, you're going to have to adjust your window so that on the x-axis you see certain values. So your lowest value here looks like a 5. So why don't you go down to, you can even go down to, let's say 3. So 3 is my x min. What's your highest value? It looks like a 13. So why don't we go to 15? And your scale can be 1. Okay, so go ahead, put that data in now that you've adjusted your window already. Okay, so if you put your data in L1, remember how to clear L1 if it has data in it, you should have 25 data points. Once again, since all of your calculations depend on this data, make sure you have it entered correctly. Okay, if we already went through how to access the box of whiskers. Whether you do the one with the outliers or without the outliers, it should still look like what I have diagrammed here in red. So I put my numbers in. To get your numbers, you're going to use the trace button. So once you graph, you can go up to trace, which is one of the gray buttons on top, and you will see you can go and hit it again and again and go from the right to the left and back to get all your values. So your low is 5, and I can see that that is the case. Your high is 13. Here is your Q1. Here is your Q3. Here is your median, sometimes called a Q2. Excuse me. a Q2. We just make this Q1. Okay, so there's my box and whiskers. Now, I said to check for outliers. So to do that, you're going to use this formula above. So let's get that done. So if I want to figure out if I have any high data that's too high, I take my Q3. So I'm going to say this is for the upper. So let's write upper here. So I'm going to take my Q3, which is 10, plus 1.5 times my IQR, which is 10 minus 7. So that's times 3. When I do that math, I am getting, what am I getting? 14.5. So if I have 14.5 and I compare that to my 13, I can see that 13 is not an outlier. Okay? Okay, so now let's check for a lower outlier. So you're going to use this formula. So take your Q1, and your Q1 is 7. So 7 minus 1.5 times 3. And if you do that math, you should be getting 2.5. Okay, you can see that 5 is not as low as 2.5. So therefore, 5 is not an outlier, and your data does not have an outlier. So you can state, based on these results, that there are no upper or lower outliers. Okay, so that is the end of this chapter.